Okay, so I'm looking at this problem, and so this is we're dealing with the central limit theorem and sample means, and the problem. Uh, so they use an example out of the book where they're talking about they give you some statistics on a population, um, where they say a certain kind of small capacitor contains a PCB that has a mean of this and a standard deviation of this. So they're saying, hey, look, here's our population. I know that the mean of the population is 48.3 parts per million. And they say that the standard deviation of this is 5 parts per million. Okay, and they want to know. So some environmental agency takes a random sample. So right, they go in, they randomly sample, they pull this out, and so now here's their little sample, and they, and hopefully it's representative of the population. Now, normally when you're doing a study, you don't know what the population's mean and standard deviation is, because if you already knew that, you'd never do the study in the first place. But we're just kind of looking at a hypothetical situation here where we're saying, okay, look, here's the population. Let's say that it does have a mean of this and a standard deviation of this. If we took a sample of size 38, so our sample size is 38, what is the likelihood of, or what is the probability of getting a sample with a mean? So I want to know what are the chances, right? So what's the probability? What's the probability of getting a sample that has a mean of 48.5 parts per million or more, right? Or more. Okay. So, so that's this. So that's the scenario, right? Here's the population. These are the actual statistics of the population, and they're saying, okay, if we didn't know those things, and if we took a sample and of that size, what are the chances, right? Or what's the probability of us getting of the average of our sample being this value or more? Okay. So now we can take a look at this, and we can run some numbers and figure this out. Okay. Thinking about this in terms of distributions, right? So here's our normal curve. Well, that's kind of a normal curve, not the greatest normal curve. Here's a normal curve, kind of. And so we're saying, hey, look, we know that for this population here that we have, we know that the actual mean is at 48.3. And they want to know, so let's pretend 48.5 is right here. 48.5, these are parts per million. They want to know, what are the chances of getting a value that's 48.5 or higher? So it's like they're looking for this area under the curve because they want to know 48 or higher. Okay. And we know that if we looked at, for example, the chances of getting a mean anywhere within the distribution is 100%. But I want to know, okay, so of that 100%, if I wanted to know what the chances of getting so let's say that I wanted to know what the chances were of getting a mean that was less than 48.3. Well, that would be easy because that would just split the distribution in half, and I could say, oh, well, chances of that are 50%. Okay, but that's not what it's asking for. It's asking about what are the chances of getting something that's 48.5 or higher. So it wants to know that part of the pie. Okay. So how do we figure that out? Right? How do I figure out how much area is in that box so that I know that probability? Okay. Well, we first do it by getting a z-score. Okay. I need to know what is the z-score at this position, okay? So to do that, to calculate a z-score, well, z is equal to your statistic minus the mean of the sample divided by the sample standard deviation. Or if we write this in terms of populations, right, it's this minus mu over the standard deviation, okay? Now we're going to make one little change to this from normal, okay? Instead of, so when we're testing a sample, we can't just use the straight up standard deviation. We have to use what's called the standard error. And so the standard error is, you see it's written like this with a little X bar. So it looks like the standard deviation symbol with this little sample mean symbol next to it. And the way you calculate that is you take the standard deviation of the population and divide that by the square root of your sample size. So for us, that's 38. So this is going to be 5. This is going to be 5 divided by the square root of 38. All right, the 5 comes from here. And get our calculator out and run these numbers. So I'm going to do 5 divided by the square root of 38. And I get 0.8111. Okay. So I have that number. And in my z-score calculation, I'm going to use this in the place of the standard deviation down there. And we do this, normally when calculating a z-score, you wouldn't do this. You would just use the regular standard deviation. But anytime we're testing a sample, which this is what this question is all about, is testing a sample. Anytime we're testing a sample, we use the standard error, okay? So let's find the z-score of this number 48.5. So to do that, well, z is going to equal 48.5 minus 48.3, right? Our number from our distribution minus the mean, then divided by, and we're going to divide by the standard error, 0.8111 equals, again, get our calculator out, run these numbers. So 48.5 minus 48.3, and divide that by 0.8111, and I get a z-score of 0.2465. Okay, so what that's telling us is what's a 2 is, so this z-score, this tells us how many standard errors or standard deviations, and really these are standard errors, we are away from the mean. And this is much less than 1, right? We're really pretty close to the mean of the population. And so now that we have the z-score, we want to move over to this table, okay? And you can find this table, it's in the book, or they should give you access to it in the problems, but this is a z-table. And you can also look these up online if you just Google z-table. What was our number? Oh, I guess I have it on my calculator right here. So the number we're interested in is 0.24657. And so now I'm just going to find it. So I'm going to go down here and write, so this is z, so 0.2, so I'm in this column, and it's a 0.24, so not this number, not this number, not this number, not this number, but it's this number, okay? And here's the really important thing, is what this number is telling you, so that number, if you can't read that, is 0.5948. Okay, so if I go back to my distribution, it's telling me that this area right here, all the area to the left of the line is 0.5984, or 59.84% of the distribution is to the left of that z-score, okay? 0.5984, so that's an important number. Well, I guess no, I could just finish the problem right here, right? So I know that this side is, that all of this side here is 0.5984, but my question was asking for what's this side of the distribution, right? Because it wanted to know, it didn't want to know what was the chance of me getting a number less than that. It wanted to know what the chances of me getting a number greater than that. And so that's the green here, okay? And so if the whole thing is 1, if I do 1 minus 0.5984, 1 minus 0.5984 equals 0.4016, okay? So that means that that green area has to be 0.4016, or the probability of you getting the probability of you getting a number that's greater than this mean of 48.5 is 40.2, right? If I round this up, right? That's 40.2%. You have a 40.2% chance of getting a number, of getting an average that's greater than the one that you had if your sample size is 38, okay? So that's what's going on. That's how these problems work. The important things to look for is, you know, what side of the distribution are you on, right? Or does it want to know what's the probability of getting something less than that number, or what's the probability of getting something greater than that z value, okay? So, that's how this all works. And let me know if I can answer any other questions for you. The other thing that you might be careful of is this number here is technically a rounded value. So if you can store this number in your calculator and then use that stored number there, you'll get a more accurate z-score, and that might be important when you're looking for the value in this table, okay? So that's kind of the one caution that I may give you, is if it's giving you the wrong answer, then be really careful of this number. Don't round it. Just use the whole thing in this z calculation, so that because that'll make your z-score really accurate, and then you can use that more accurate z-score here when you go looking around in the table to find, oh, there's 0.24, and you know what, maybe I should have used 0.25, because this 6 technically should have forced that to round up, so maybe I should have used the 5 and come over here and grabbed this one, which would change this answer slightly, right? Because instead of doing 1 minus 0.5981, I would have done 1 minus 0.5987, and that would have changed my final answer a teeny bit, right? I mean, if I do that, that's 1 minus 0.5987. Then I get 0.4013. So, which is a teeny bit different, right? It's not that much different, but it is a teeny bit different than what I had before. Anyways, that's how all this stuff works. And let me know if you have any other questions. And thank you so much.